Section 4.4 is where we start to deal with solution stoichiometry. And one of the things that we deal with solutions is understanding what is in the solution and what is not. The solution is made up of a couple of parts, as we'll talk about in a moment: the solute, which dissolves, the solvent, where the solute dissolves into, and the solution, which is the combination of the two. What we've seen as a solid forming previously in a lot of the experiments we've done in lab with the copper and so forth, is the solid that forms in a solution is not actually part of the solution, it's part of the precipitate. That kind of spawned one of the first chemistry jokes I've actually ever heard back when I was a kid. A comedian named Stephen Wright had these great one-line things where he'd just say some weird line or other. It was a weird observation, and his old joke was, well, if you aren't part of the solution, you're part of the precipitate. Making fun of the if you're not part of the solution, you're part of the problem line of conventional wisdom. But the three parts that we have to a solution: one is the solute. That's what you have the least of. The solvent is what you're going to dissolve the solute into, and that's defined more rigorously as whatever you have the most of in the mixture. Now, usually that's going to be water for this course. The solution is what we call the combination of solute and solvent together. So we need to know this pretty rigorously because we're going to talk about a number of different types of concentration units, and they're going to be defined based on these three parameters. Well, the first concentration unit is going to be called molarity, and that's abbreviated with a capital M. So be careful not to make that look like a lowercase m, or to make meters look like an uppercase M, because we don't want to confuse the two. One's meters, this other one is molarity. Now, if we're going to refer to a solution and its concentration, we'll say that it has a certain molar concentration. Now, all that really means is the moles of solute per liter of solution. And this basically gives us a way to dispense some volume of that solution and obtain a specific number of moles for having added that volume of solution to a reaction. Makes it a little bit easier to measure out chemicals. Instead of a scale, you're using a pipette or just a graduated cylinder, for instance. So how does this work? Well, let's look at a really simple example. If I had 1.25 moles of sodium chloride, that would be the solute, that's the smaller amount, solute, and I add enough water to make the solution have a total of 500 milliliters of volume. So that's the solution volume. What is the molarity? Remember, it's moles per liter. So that means I have 1.25 moles sodium chloride in 500 milliliters. So let's turn that into liters. Digit there we go. So 0.5000 liters of solution. So that's going to give me a total of 2.50 molar sodium chloride. Okay, so that big M just stands for moles of solute for every liter of solution. Okay, but we abbreviate that as capital M. So if I need to calculate a molarity for a solution, I just calculate the number of moles divided by the volume of the solution in liters. Now, the critical part here is that this is moles of solute per solution, so the total of the combination of solute and solvent. This is not solute and solvent. I can't just add a liter of water to 1 mole of solid and get a 1 molar solution. I'll actually end up with more volume than a liter if I combine those two things together. So how do I get a 1 molar solution? Well, the direct way is I take a flask, like a volumetric flask, which is a very precise flask for measuring liquid volumes, and I add in enough salt, sodium chloride, to give me 1 mole of that sodium chloride, and then I add water and dissolve, and I add until I get to this little mark up here, and that mark indicates exactly 1 liter, usually 2 plus or minus 0.01 liters. So it gives you some good sig figs there. So when it's up to a total of 1 liter, I've added less than 1 liter of water, but I have now 1 liter of water plus sodium chloride volume. And so that's a 1 molar sodium chloride solution at that point. Let's take another example. What if I weigh out 25.5 grams of potassium bromide and I stick it in enough water to get to 1.75 liters of total solution? What's my molarity? So if I say molarity, I know I want moles of KBr for every liter of solution. So I just have to find both of those things. Well, I have 1.75 liters of solution already. So that'll go on the bottom of my ratio. And let's calculate the number of moles of potassium bromide by grabbing a periodic table and adding this up. Potassium is 39.098 and bromine is 79.904. So together, 9.904 plus 39.098, I get 119.002 grams of KBr for every 1 mole of KBr. Good. There's my conversion. Excellent. Okay, so 25.5 divided by 119.002 gives me 0.2143 moles of potassium bromide. So that's what I put down here. Remember, don't round to the end. So divide by 1.75, and I get a 0.122 3 sig figs molar KBr solution. Okay? So not a difficulty. I mean, there's some converting going on, and remember at the beginning, I don't know if you believe me, but I'm sure you do by now, there's going to be a lot of converting going on. This is part of where we're starting to see a lot of that converting happen. Well, how do I use molarity? Now that I know how to calculate it, how do I use it? Well, all it is another conversion factor. It makes it easier to write it in a paper or an article by putting it on the same line, just using one letter. But in reality, it is a conversion factor. So 5 molar sodium chloride means 5 moles of sodium chloride for every 1 liter of solution. Or just like we can do with every conversion factor, we can write it upside down if we need to cancel out the other set of units. And we can use that however we need to convert back and forth between solution and moles of sodium chloride. So let's try it. Say I have 250 milliliters of a 0.500 molar sodium chloride solution. How many moles of sodium chloride are obtained? Well, at first you're kind of like, wait, there's no ratio. Yeah, there is. It's hidden in the molarity unit. Okay, so that's what this 0.500 molar sodium chloride means. It just means this, in whichever direction we need it to be in order to convert. So I have 250 milliliters of solution. If I had liters, I could get to where I want to be, which is in moles. So I want moles of sodium chloride over here. I'm starting with 250 milliliters of solution. Let's see where I can get to. So I need liters. So I'll convert the liters. Milliliters cancel. I'm left with liters of solution. Now I can use this because liters are on the bottom. And there we go. My units of liters of solution cancel. I'm left with moles of sodium chloride, which is what I want. So 250 divided by 1,000 times 0.5, I would get 0.125 moles of sodium chloride. And 3 sig figs is what we can justify with that number. All right, well, let's try another example. If I need this many moles of sodium chloride, how many milliliters of 0.350 molar sodium chloride do I need? So keep in mind, and this isn't a bad practice, is wherever you see molar, just write out what it really is so you don't get confused or forget that that's what this translates to. All right, where do I start? Start with the only thing that's not a ratio is usually a good plan if you're not sure where else to go. But I have 0.100 moles of sodium chloride. Where do I want to get to? Milliliters of solution. Okay, so that's my final answer over here. So I got to get closer to that. Well, I got moles and liters of solution here, so I can use that conversion. Liters on top because that's what I want. Moles on the bottom because that's what I want to get rid of. Excellent. And now that moles of sodium chloride have canceled, I have liters of solution. So that means 1,000 milliliters of solution. For every 1 liter of solution, just converting to milliliters from liters. Liters of solution cancel. I'm left with milliliters of solution. Excellent. 0.100 divided by 0.350 times 1,000, I would need 285, more or less, 286 it looks like if I round properly. Single line cross out, 286. There you go. But 286 milliliters of solution is what I need to get 0.1 moles of sodium chloride. Well, does that make sense? That's about a quarter, and maybe a little more. And this is 100, or 0.100 moles is a little less than a quarter of 0.350. So yeah, that makes sense. If I had a whole liter of this solution, I'd have 0.350 molar. But I don't, so I don't have 0.350. It all makes sense. This equation is almost worth getting as a tattoo. This is used so often in industry, in research, in this class, in your next class for chemistry, in organic chemistry later on, in biochemistry after that. This one's used all over the place. Well, what does this mean? It means my initial molarity times the initial volume of a solution is going to be equal to the final molarity times the final volume. So if you're diluting something from an initial concentration, you have a certain amount of it, and then you fill up the solution with some more water. You can calculate what the final molarity will be, or initial volumes to get a final molarity. You can do all sorts of things with this equation. So let's try it with some examples. I have 10 milliliters of a 12 molar hydrochloric acid solution, and they're placed in a flask, and enough water is added to make a full liter of solution. What's the new concentration? As soon as you recognize this is a dilution type problem, you want to get M1V1 equals M2V2, write that up there. Now the only thing you have to do correctly is link the things that are connected. I initially have 10 milliliters of 12 molar hydrochloric acid. Those are linked. Doesn't matter if you actually put them as M2V2 or those are M1V1, they just have to be on the same side of the equation. That's critical. Okay, so 10 milliliters times 12.0 molar HCl equals, all right, 1 liter, and new concentration is X molar. All right, well, 1 liter, 10 milliliters, this doesn't cancel unless everything's in the same units. So I want to solve for X, but if I divide here, I'm not going to get the same units. So why don't I go ahead and put this in liters. There we go. So now we can rewrite this as 0.0100 liters times 12.0 molar hydrochloric acid is equal to 1 liter times X molar hydrochloric acid. So an unknown new diluted concentration. So solve for X. So 0.01 times 12 divided by 1 is 0.12, and that's equal to the molarity of hydrochloric acid I have at the end of this process. So I have 0.12, 3 significant figures, 0 molar hydrochloric acid after this dilution. Always check that this makes sense. I start with a high concentration and add a bunch of water. The concentration should go down at this point. It should get more dilute, less concentrated. If you found that the concentration went up instead in this type of a problem, you probably didn't link the right two things together. So look at it again, see if you maybe have to link it differently. But if you add water, the concentration goes down. Let's look at another example. Now in this one, we're going at it from a slightly different angle. How many milliliters of an 18 molar sulfuric acid solution are required to make 500 milliliters of 1 molar sulfuric acid? All right, so let's link. The 500 seems to go with this 1 molar. So 500 milliliters and 1 molar are together. Doesn't matter if they're the first one or the second one. It really doesn't matter. 2SO4. Good. And this is equal to X number of milliliters of, so times 18.0 molar. H2SO4. So you might be thinking, all right, this is moles per liter, so in order for this to cancel nicely, this should be in liters. Nope, that's not really the case. It doesn't matter. I mean, ideally, yes, but if you change this to liters and this other side to liters, you're changing everything by the same ratio. You're not changing the solution to this problem. Okay, so as long as the units are the same on both sides, you're fine. Just keep track of your units. So I'm going to solve. 18 molar, 18 molar. So 500 times 1 divided by 18 gives me 27.77, etc. is equal to X milliliters. See? Keep track of the units. So what do I have? Two significant figures. So to get 1 molar sulfuric acid and 500 milliliters of it, I better take 28 milliliters of 18.0 molar sulfuric acid. Okay, so does that make sense? I want to take some really concentrated stuff and make it dilute. So I should need a small amount of the concentrated stuff into a larger amount of water to dilute this down to a lower concentration. And that's what it says I'm doing. If you got something really big and it said, yeah, I need 3 liters to make 500 mil of something else, you probably linked the things up wrong again. So just keep track, make sure that everything makes sense, and you should be fine. One more layer. So solution stoichiometry. This may seem like it's a lot more, but in reality, all we're doing is going from molar and some number of milliliters of a molar solution, right? That will give us moles. And for stoichiometry, once we have moles, we can go to moles of something else, and then we can go right back to milliliters of some molar solution. Okay? So effectively, milliliters to moles using molarity, moles to moles using the balanced equation, the chemical equation, just like any stoichiometry calculation, then moles back to milliliters using the molarity again. All right, let's try it. So we have hydrochloric acid and calcium hydroxide reacting to form calcium chloride and water. This is an acid-base neutralization reaction. So we can ask a question like, well, how many moles of this calcium hydroxide will I need if I'm trying to neutralize 20 milliliters of 0.5 molar hydrochloric acid? Well, you'd be all over this problem at this point if instead of this I just told you you had some number of moles of hydrochloric acid. But given volume and molarity, which is just, remember, moles for every volume. Okay, so I have a ratio here between moles and volume. I just have to use it to get moles. So that's where we'll start. And again, if you're not sure where to go with these problems, look for something that's not a ratio. Molar is a ratio, so don't start with this number. 20 milliliters, not a ratio. Probably a safe bet on where to start this problem. Alright, so 20 milliliters of HCl solution. Label, 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 all sorts of labels. Otherwise, there's going to be a lot of things that are very similar. You'll get confused. Alright, I want moles. Because once I have moles, milliliters to moles, right, our schematic here, I can get the moles of what I want. And if I had to, I could get back to milliliters. But I don't for this one. I can stop at moles because that's what it's asking for. So milliliters to moles, that's through molarity. My molarity is in moles per liter. So if I had liters, I'd be set. Oops, stray marks. There you go. So I need to just be in liters to take advantage of the molarity. Okay, so now I have liters of hydrochloric acid solution. So now I can use the molarity to go to moles. Okay, so liters and solution cancel out. And now I have 0.5 moles, so times 20 divided by 1,000. I have some number of moles of hydrochloric acid. So I'm right here. Now I go to moles of the thing that I'm really interested in, the calcium hydroxide. So there's 1 calcium hydroxide mole for every 2 hydrochloric acid moles. So moles of HCl cancel out, and I'm left with moles of calcium hydroxide, which is what I want. Excellent. All right, so 20 divided by 1,000. So right here, after this calculation, I'm at 0.0200 liters. Okay? Times 0.5. So right here, I get 0.100 moles of HCl. Okay? 1 calcium hydroxide for every 2 HCl's. So I'll divide by 2. Right now I'm at 0.00500 moles of calcium hydroxide. Oh, excellent. That's what I wanted. Sig fig wise, I'm limited by this 0.50. So 0.05, one extra 0. There we go. 0.0050 moles of calcium hydroxide. Not a lot more difficult that it can get. The only additional possibility we could have is milliliters all the way back to milliliters. Right? So milliliters to moles, moles of what we really wanted, back to milliliters. Let's try it. So how many milliliters of calcium hydroxide solution, and we have a concentration of it. That's just a conversion. We'll use it whenever we need that conversion. Okay. I needed to neutralize 20 milliliters of 0.50 molar HCl. So again, this is just a conversion. Write it out. Good. All right, so now that nothing can fool us, let's see, where do we start? There's numbers everywhere, right? Don't start with the ratio. Start, keep calm, start with the thing that's not a ratio. Okay, so 20 milliliters of hydrochloric acid solution. Good. So we need to go from milliliters to moles. So to do that, I'm going to need to be in liters. So liter, milliliters. Good. Now I'm in liters of hydrochloric acid solution. So now I can go to moles. Good. So now I'm in moles of hydrochloric acid. Not solution, moles of hydrochloric acid itself. Now I can get to moles to moles. So 1 calcium hydroxide again. Looks pretty similar, doesn't it? Every 1 hydrochloric acid from the coefficients in the balanced chemical equation. 2. I said 2 and wrote 1, didn't I? Erase. There you go. There you go. So now, after this, hydrochloric acid's gone. So I'm in moles of calcium hydroxide. And now we want milliliters. Well, I know liters of solution per mole of calcium hydroxide, so I'll use that ratio. 1 liter of solution for every 0.500 moles of calcium hydroxide. Got to be getting close to the end here somewhere, right? How many milliliters? All right, well, I'm in liters of calcium hydroxide solution right now, so back to milliliters. Good. So I just multiply this through. So 20 divided by 1,000. So after this first step, I have 0.0200 liters of hydrochloric acid solution. After this next step, I have 0.0100 moles of hydrochloric acid, because liters of solution have canceled. After this next step, I'm going to have 0.00500 moles of calcium hydroxide, right? Because hydrochloric acid moles have canceled out. Now after this step, we will have liters of, and specifically 0.0100 liters of calcium hydroxide solution. Good. And now after this step, we will have times 1,000, 10 milliliters, 2 sig figs because of this. That wasn't getting any better. All right, 10 milliliters. Raise. So at this point now we have 10 milliliters of calcium hydroxide solution. Okay, and that's our answer. And then we stop and we say, does this make sense? Well, I need 20 milliliters of hydrochloric acid. They are the same concentration, so the only factor I have here is that I need twice as much hydrochloric acid as calcium hydroxide from the equation. Since they're the same concentration, I can look at that ratio. Well, I have twice as much hydrochloric acid as calcium hydroxide, so that fits. And that's pretty much as hard as this can get.